So let me start. Let me ask y'all, is there any questions before we jump into this? We good? All right, let's take a look at what we're looking at today. All right. I mean, that's how I like to do it, you know. I'm an Excel head. Yeah, yeah. Yeah, huge statistics head, yeah. All right, so we all know that a flat mirror enables us to see an accurate image of ourselves and whatever is behind us, right? Good. Huh? Star, like number 8. Yeah. Um, what was behind us? When we tilt the mirror, the image we see may shift horizontally or vertically. But what happens when we bend a flexible mirror, like a carnival funhouse mirror? It presents us with a distorted image of ourselves, stretched or compressed horizontally or vertically. In a similar way, we can distort or transform mathematical functions to better adapt them to describing objects or processes in the real world. In this section, we will take a look at several kinds of transformations. So that's what we're getting into today, transformations. All right. And we're going to go step by step through all of this. All right. Let's start off with vertical and horizontal shifts. All right. So graphing functions using vertical and horizontal shifts. Often, when given a problem, we try to model the scenario using mathematics in the forms of words, tables, graphs, and equations. One method we can employ is to adopt the basic graphs of the toolkit functions that we talked about before to build new models for a given scenario. So there are systematic ways to alter functions to construct appropriate models for the problems we are trying to solve. Okay. So we're gonna start off basic and then we're gonna build it up from there. All right. So first thing I want to start with, we're going to start with identifying vertical shifts. All right. So one simple kind of transformation involves shifting an entire graph of a function up or down, right or left. The simplest kind of shift is a vertical shift, right? So moving the graph up or down. Because the transformation involves adding a positive or negative constant to the function, that's the key right there, to the function. In other words, we add the same constant to the output value of the function regardless of the input. So for a function g of x is equal to f of x plus k, right? The function f of x is shifted vertically k units, all right? So let's take a look at that. So let's say I have this function right here, right, which we know is the cube root of x, right? If I add a constant to it, let's just keep it simple. Let's say I'm adding 1 to it, right? It's going to shift the graph up 1 unit. That's all that's happening, shifting the graph up 1 unit, right? So this is a vertical shift by k equals 1 of the cubic function f of x is equal to the cube root of x, right? I'm adding 1 to it and it's shifting it up 1 unit, right? But more specifically, I'm shifting the y coordinates. You know how you have the x coordinate and the y coordinate? I'm shifting the y coordinate up 1 unit, or in general k units, whatever. Hmm? All right. So to help you visualize the concept of a vertical shift, consider that y equals f of x, right? Therefore, f of x plus k is equivalent to y plus k. So every unit of y is replaced by y plus k, right? Value increase or decrease depending on the value of k. The result is a shift upward or downward of the graph. Okay. I feel like somebody in the back ain't get it. So let me just say it one more time. Real quick, real quick. Vertical shift. Right. right? It's going up.
Like that,
Mhm.
when maybe on both sides.
Yeah,
Now it's 1 plus 5, so it'll start at 5 plus.
exactly, exactly. All right. So one more time, vertical shift. Given a function f of x, a new function g of x is equal to f of x plus k, where k is a constant, is a vertical shift of the function f of x. All of the output values change by k units. If k is positive, the graph will shift up. If k is negative, the graph will shift down. That's it. All right. We're just keeping it simple, keeping it simple. Let me give y'all a little bit of sauce real quick. Y'all know I like to spill the tea in this class, right? All right. So this is how, given a tabular function table, right? Create a new row to represent a vertical shift. This is how you do it. Step one, identify the output row or column, the Y, right? Step two, determine the magnitude of the shift. How much are you shifting it by, right? Step three, add the shift to the value of each output cell, right? If you add a positive value for up or a negative value for down, all right? Let's take a look at an example, right? I can't keep holding on to all the fun. Gotta share the wealth. Gotta share the wealth. All right. So shifting a tabular function vertically. A function f of x is given in the table. Let's create a table for the function g of x where f of x is going to be subtracted by 3. So I'm going to shift this table down 3 units. Right? All right. What's happening here is that my x inputs are the same. Inputs are the same. No change. No change, right? But for the g of x, this is going to be f of x minus 3. Let me just verify that. Yep, f of x minus 3, right? So what I'm going to do, I'm going to take all my answers for f of x. I'm going to subtract 3 from it. All right. So let me do it real quick. 1 minus 3. Oh, y'all got to help me. I'm bad at math. This 1 minus 3. -2. Thank you. Thank you. 3 minus 3. Oh, that's the hard one right there. What's that? 0. Very good. Very good. All right. 7 minus 3. What's that? 4. Good. And then 11 minus 3. What's that? 8. Very good. Right. So that's my new g of x. I'm just going to write it again just to make it pretty. All right. It's the same thing as above. I'm just writing it again just to make it pretty. So -2, 0, 4, and 8. That's it in a nutshell. So there's going to be some kind of number. You're just going to change the y value of it, and then that's it. Is any questions on it? Anybody?
Basically, identify the vertical shift we're done. Identify the vertical shift. You identify the bond.
Pretty much. Yeah.
I figured.
That's all I'm doing. Well, yeah. Well, this one is going down because it's -3. My bad. My fault. Yeah. Hold on. Let me just pull that right. Yeah. This particular one just going down 3. Second.
Okay, you scroll up.
Uh, yeah. My fault. Oh, you mean this one right here?
A little bit further.
This?
Ah,
Yeah. As long as you can remember, you just change the Y value, the output, we good to go with the vertical shift. Now we got something else to talk about afterwards. Let me know when you're done. Hmm. Yeah. Well, technically it's plus K, you know. If we want to talk theoretically speaking, right? Like,
You just did -3.
yeah. The thing is that, like, how can I say this now? K could be positive or negative. It don't matter, right? But the plus sign is always in front of it. So if it's negative, it just goes down. If it's positive, it goes up. Yeah.
All right.
I'm trying to make like a general statement, but I'm like not forming it right now in my head. That's why I'm not saying it. All right, before we move on, let me just make a special note real quick. So I'll make a special note. Oh, 1 second, hold on. Sorry about that. Try that one again. There we go. All right. Oh, apologize about that. Got away from me. This joint be trying to shift now, and I'm in the middle of the lesson, yo. It's like that. All right. Real life application right there. All right. Anyway, so analysis, right? So as with the earlier vertical shifts, right? Notice that input values stay the same and only the output values change. I want to make that note. All right. Little special note. All right, let's flip the script. So I want to talk about horizontal shifts. All right, so now we're going to be identifying horizontal shifts. We just saw that the vertical shift is a change to the output or the outside of the function, right? We will now look at how the changes to the input on the inside of the function changes its graph and meaning. A shift to the input results in a movement of the graph or of the function left or right, all right, in what is known as a horizontal shift, right? So here goes a little graph to show you what I mean, right? So same thing, we have the cube root of x, blah, 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 right? But in this scenario, I'm adding 1 to the input, to the inside. So this is like f of x plus 1, right? So that's going to shift my graph a little bit to the left, right? And if it was f of x minus 1, it would shift it to the right, right? So just to go over it, the figure 5, horizontal shift of f of x is equal to the cube root of x. Note that x plus 1 means that the h is equal to -1, which shifts the graph to the left. That is towards the negative values of x. All right. So for example, if f of x is equal to x squared, then g of x equals to x minus 2 squared is a new function. Each input is reduced by 2 prior to squaring the function. The result is that the graph is shifted 2 units to the right because we would need to increase the prior inputs by 2 units to yield the same output value as given in f. All right. So we're going to see some more of this. Yeah, the horizontal is a little bit more tricky than the vertical because it's on the inside. All right, horizontal shift. So given a function f, a new function g of x is equal to f of x minus h. That's our key formula right there, right? G of x is equal to f of x minus h, where h is a constant, right? It's a horizontal shift of the function f. So if h is positive, we're gonna shift to the right. And if h is negative, we're gonna shift to the left. But our general function is f of x minus h. That's the key you got to remember there. General function, f of x minus h. All right. Let me make a special note real quick. All right. Yeah.
Right.
It is that way because of the general formula we got f of x minus h. Right? As long as you always remember that part. If h is negative, you're going to the left. If h is positive, you're going to the right. All right? Yeah. We gonna see that. We gonna see that. You know. So the horizontal changes or inside changes affect the domain of the function, the input, instead of the range, and often seems counterintuitive, right? So just wanted to say that one statement. But just to elaborate on what you were saying before, though, right? We have our general formula, g of x is equal to f of x minus h, right? Now, let's say in the case where h, right, is less than 0. So I got a negative h, right? A negative h right here, right? So what does that mean? I'm trying to think how I can make this like more nicer. So what does that mean, right? That means that for the g of x, I have f of x minus h, right? This is why you're saying, "Oh, I thought when it was positive, I'm going to the left," right? This is the reason why, because a negative and negative make positive, you know? But the formula stays the same. For h greater than 0, right? So we have positive h. You know, let me just erase the so. Positive h, right? This one is g of x is equal to f of x minus, say, positive h, right? Put that in parentheses right there, just like that, right? So in that one, it looks like you have a minus h, but you're really moving to the right. This is the reason why, you know? Before we move on, let me just give y'all a little tea. All right. All right. So given a tabular function table, create a new row to represent a horizontal shift. All right. So here's how we do it. Step one, identify the input row or column, depending on what you have. Right. Step two, determine the magnitude of the shift. Right. And step three, add the shift to the value in each input cell. All right. In each input cell. Let's take a look at an example. Let's take a look at an example real quick, real quick, real quick. So shifting a tabular function horizontally, a function f of x is given by the table. Create a table for the function g of x, right, equal to f of x minus 3. All right. So, 1 second. Nickelodeon. Interesting. I didn't do this one. 1 second, y'all. 1 second. Bear with me 1 second, y'all. 1 second. All right, sorry about that. So let's do this now. So what's changing in this? My input is changing, the X, right? So just to recap, right? My X's that I have right now, 2, 4, 6, 8, right? Now what's happening is I'm gonna subtract 3 from them, right? So this is gonna be like X minus 3 right here. So this one is gonna be 2 minus 3, call that -1. 4 minus 3, call that 1. 6 minus 3, call that what, 3? And then 8 minus 3, call that 5, right? All right. Just to make it pretty, I'm going to rewrite it one more time. So x minus 3, this became -1, 1, 3, and 5. And then the g of x is actually going to be equal to what the old f of x was equal to, right? So in other words, the y values didn't change, just the x values changed, right? So the y values I had before were 1, 3, 7, and 11. I copied it from right here if you're wondering where I got those numbers from. Okay. Questions on this? Anybody?
So why am I getting changed? Or not trying to form of fully affected the exercise?
Exactly, right? So horizontal shifts only affect the input, right? The x's, they don't affect the y's. Right?
So but
Mhm.
your X equal X axis of affecting,
Say it again, the g of x equals the x-axis?
but I see G of X.
Mhm.
Right, they're not forming affects things on exercise. Or affects the domain.
Depends on the question. Like for this particular question, I have this g of x is equal to f of x minus 3. That's why. And the x minus 3, see, it's like it's inside the input part. So that's why that's happening. Mhm. It'll tell you. It'll tell you. So if the -3 in this case, right, is inside the parentheses, you're changing the input, the x values. If it was outside, say it was f of x minus 3, now that's the vertical shift. That's changing the y value. So anything outside the parenthesis, that's going to be the y. Inside the parentheses is the x. The y values, yeah, yeah. Mhm. That's true.
Every time I see an F of X,
Hmm.
F of X is Y.
Hmm.
It's a change in the base that when it's myself.
Right, yeah. So I don't know if this helps, but graphically speaking, this is what's happening. All right. So the blue that you see right here, that was our original equation that we had. That's the f of x, right? The red is our new equation. That's the f of x minus 3, right? And we shifted each point 3 units to the right, right? So you see that they moved in terms of the x-axis, but not the y. They had the same y value, right? Same y value, just got shifted a little bit to the right, you know. That's it. That's what is called a horizontal shift. All right. Questions on this so far? We did like 2 topics just now. All right. All right. Let's keep it moving. We got more to talk about. Yeah, of course.
Just to reiterate.
Mhm.
Horizontal shifts, fully affect changes, X value.
Yeah.
Function.
Yeah.
Vertical shifts, but our changes in our Y.
Yes, no, just the y,
Just.
just the y.
Just
Yeah,
both.
yeah.
Vertical.
Nah. Yeah. But we building up to something that involves both though. Yeah. Yeah, we just going step by step. I'm just going a little slow with it. Yeah. All right, so here go another example real quick, all right? So this is identifying a horizontal shift of a toolkit function, right? So we got figure 8 right here represents a toolkit function f of x is equal to x squared. We all know this, palabra, right? So relate this new equation g of x to f of x and then find a new formula for g of x, right? So blah, blah, blah. We know that f of x, just leave that right there. I'm gonna write on the bottom. We know that, you know what, let me change the color. Change the color. I'm gonna get fancy now. I'm gonna go rainbow. All right. So we know that f of x, right, is equal to x squared. Right. That's the original function. Right. That's the one that looks like this. Right. Sure. So this is it. So we're looking for our new function g of x. All right. So g of x would be the blue. The rainbow is the original equation. All right. So now let me switch over to the blue real quick. Right. I want this new function g of x. So I want to know what is the equation, right? Here's what I want you to focus on. Mm, let's go with the BCC green right here, right? In the original function, that's the origin, right? That's 0, comma 0. In this shifted function g of x, right? What's the origin right here? No, 2 comma 2 comma 0, right? So this was shifted how many units? 2 units, right? So what's the equation? Tell me. Plus 2? So remember our general formula. Let's go back to that real quick. I'm gonna do that in up here. G of x is equal to f of x minus h. All right, cool. All right, so now give it to me now for the go back to the blue. This is gonna be what? It was given before up here. I'll show you. Yeah. All the way up here. Right here. No. I'm showing you where it came from. G of x equal to f of x minus h. That's where it came from for the horizontal shift. But I know that the original function here is x squared. So what am I gonna write inside of this? It's gonna be something squared. It got shifted where? To the right or to the left? To the right, right? So this is going to be x minus how many units to the right? 2, right? So positive 2. Like that. Putting it together now, it becomes what? X minus 2 squared. Mhm.
Wow.
Huh?
Right, so it. But my thing was square, and it's automatically, I'm getting to what I. Make it to not very.
Don't think of it like that. I get what you're saying, but don't think of it like that. So what I did was I used the original function I was given, right? So g of x equal to f of x minus h. And I just put in how many units the h moved. So it moved positive 2 units, right? If it was to the left, I would have put in negative 2, for example, And a negative becomes a, right, and then that would have been it. Hmm? Where I got x squared from? The origin, 0, 0? That was always there. Yeah, I just chose any random point. I could have chosen any point on this graph. I like 0, so I just chose it. I hear you. Like to make the original equation you're saying. But they gave it to us. See, f of x equals x squared. No, x squared is the original parabola, the rainbow parabola that I have there. Right? I just focused in on the origin to make it easy. I could have used any point on that graph, right? Like I could have found a similar point on both and then just compared them. The origin was just the easiest one because 0, 0.
They, they define,
Mhm.
where X is. Like, you know, like you said, X squared. So, what started the origin for them, because, you know, they had added some things to it. Like X squared, no, that's not, so.
Like if they had a multiple shift. Yeah. You're right. Yeah, that'd have been something different. It's a different strategy.
No, like you said X squared.
Hmm.
I'm thinking of X as a coordinate.
Okay.
Not, well, it's not X squared,
Yeah.
it's not BX squared.
Right.
X squared, so the first X begins at 0.
Right. Mhm. Another way you could do this, right? So let's say that you didn't like the graph, which is fair, right? Let's say you didn't like the whole graph thing, right? You could have went back to this whole table thing that we did up here, right? They gave you the function f of x is equal to x squared. You could have wrote out a couple of points, right? Like you could have plugged in 1, plugged in 0, plugged in 1, and you would have had a table just like this with x's and y values. And then you just do the same shifting that you were doing over there, right? It would have been the same answer. Mhm. This is just using a graph. That's all.
Yeah, and it says, on the graph, it says FX that term.
Yeah. But you know what the advantages of using the table too? Like, let's look back at this example real quick. If you notice, right, with the table one, I didn't whip out that like general formula x minus h, right? I just went with whatever they told me, right? G of x is equal to f of x minus 3, right? And then I just changed the x's that was there. That was it. And the y value stayed the same. That's how that if you want, you can do it like that. You know? The only difference is, right? You see like how this graph has dots? You would have to identify some points on this and just like graph it again, you know? Just graph some points on it. And that's it. Mhm. Connect the dots.
But I think one of that, so. More complicated question.
Nah, nothing complicated.
Why is it negative?
-2? Oh, because the original function, g of x is equal to f of x minus h, right? Like that's just the general formula. So the h is positive, right? So then that means that it gets -2.
Oh, not eight,
Uh,
like,
do the opposite. So positive, yeah, positive, go towards the left, negative, go towards the right.
I think eight, like, basically.
It is.
Now, subscribe says, for H two. So
Yeah.
you put in parentheses for positions that's positive two position.
Right.
Now, that's.
Yeah. That's another way to do it too. All right. That's horizontal shifts. You will see more of them in your homework. All right. Let me just make a special note real quick before we move on. All right. So to determine whether the shift is a +2 or a -2, consider a single reference point on the graph for a quadratic. Looking at the vertex point is convenient. In the original function, f of 0 is equal to 0. In our shifted function, g of 2 is equal to 0. To obtain the output value of 0 from the function f, we need to decide whether a plus or minus sign will work to satisfy g of 2 is equal to f of x minus 2 equal to f of 0 equals 0. For this to work, we need to subtract 2 units from our input value. All right? So blah, blah, blah. What does that mean, right? In my original function, right, f of x equals x squared, if I plugged in 0, I got back out 0. In the shifted function, right, for the vertex, I plug in 2 and I get out 0, right? So what do I have to change the function, the inputs to, so that when I plug in 2, I'm going to get back out 0, x minus 2. So when I plug in 2 now, 2 minus 2, that's 0, is giving me the output. That's another way to think about it. I know, little tricky, but when you see it in the homework, it'll make sense. Nah, it don't make sense.
So I mean, that's exactly.
Right. I'm okay with that too. All right, let's do a harder example. All right, interpreting horizontal versus vertical shifts, right? Excuse me. The function g of m gives the number of gallons of gas required to drive m miles, right? So let's interpret g of m plus 10. What does that mean? So g of m is the number of gallons that you need to have in the car. M is the number of miles you're gonna drive from those gallons that you have. Right? So if I say g of m plus 10, what does that mean? Like I'm adding 10 more what? Not miles, 10 more gallons to the tank, right? Because g of m is the gallons of what's it, oil or gas? The gallons of gas that's inside of the tank, right? What does g of m plus 10 mean?
Changes the miles.
Right, so I'm adding 10 more miles, right, to the gallon. Right? Question? Make sense?
It's
All right.
like like a cycle where it says G, let me see, M plus 10.
Right.
And the other equation from the G is pretty much like f of x.
Right.
So
Exactly.
in the parentheses,
Mhm.
it's affecting the x.
Right.
If it's not in the parentheses, it'll be affecting the y, or in this case, it'll be affecting the G.
Right. Exactly. That's exactly it. Yeah. Yeah. Mhm. Right. Mhm. Yep. The usual gallons that you have, you're gonna put 10 more on top of that. And the other one is like I'm gonna put 10 more miles on top of the gallons that I have already. All right, all right, all right. Fun stuff, fun stuff, fun stuff. Want to try another one? That's it. Just talk it out. Just interpreting. Yeah. I always say in mathematics, right? When in doubt, write a paragraph. It's one of those paragraph questions. Yeah. Sometimes y'all get partial credit when y'all doing your math problems and stuff. Like if y'all don't know how to do it, but you could think through it, right? You get partial credit for that. You know? So just my little tip. All right, let's look at this one. Given that the function f of x is equal to the square root of x, right? It says graph the original function, right? F of x, and the transformation g of x is equal to f of x plus 2 on the same axis. Is this a horizontal or vertical shift? And which way is the graph shifted and by how many units? All right. Without me even graphing it, tell me, what is this? It's going to be a horizontal or vertical shift.
You
What is it?
right?
Horizontal. Why?
What's this complex?
It's affecting the x, the input. It's affecting the input. All right. Is it going to be shifted to the left or to the right? Left. To the left. All right.
And
Good.
if you put the x plus 2 inside, I have no idea what that's called. Put it inside there, we still have to get it to the five, so regular number.
Right.
So, see how the last equation we had x minus 2 squared,
Mhm.
technically that's the same thing here. Because it needs to get back to being a real number.
Right. Mhm.
What is that for?
Which one? The square root of x? Yeah.
Yeah, that's the word for it.
Yeah.
Right.
Yeah. If I'm not mistaken, let me think. It's 2. No, shoot. X is 4. That's 2. It's 9. That's 3. So from our toolkit, this should be our original graph, something like that. Right? And then we shifting it 2 units to the right, right? To the left. All right. Just checking, just checking, just checking. Y'all have me scared there for a second. Y'all have me scared there for a second. All right. So there we go. That'll be our shift to the left. I'm really bad at drawing, but that should actually be on the same line. All right. And then that's it. In other words, that's 0, 0, right? So 2, 2, 2. It's going to the left. Going to the left. This point right here, yeah, yeah. This point here would be -2 comma 0. All right. Because the idea is that I need to plug in a number that's going to give me back that same y value. So -2, give me back that 0. Mhm. That's not a really nice graph. I'm really bad at art. That's why I didn't major in art. Yeah. I mean, some of y'all got good calculators. Y'all could get better pictures than this. All right, let's take this up a notch real quick. So I want to combine vertical and horizontal shifts. All right. So now that we have two transformations, we can combine them together. Vertical shifts are outside changes that affect the output y, right, on the y-axis and shift the function up or down. Horizontal shifts are inside changes that affect the input on the x-axis and shift the functions left or right. Combining the two types of shifts will cause the graph of a function to shift, excuse me, up or down and right or left. All right. I want to give y'all a little bit of tea real quick. All right. So given a function and both a vertical and a horizontal shift, we want to sketch the graph. So first, what do you want to do? You want to identify the vertical and horizontal shifts from the function. Step two, the vertical shifts results from a constant being added to the output. So that's going to move the graph up for a positive and constant and down for a negative constant. The horizontal shift results from a constant added to the input. That's going to move the graph left for a positive constant and right for a negative constant. All right. And then step four, apply the shifts to the graph in either order. Right. The key thing to remember about that is that it doesn't matter which one you do first. You want to do the vertical one first, go ahead. Or if you want to do the horizontal one first and then do the vertical, go ahead. No pressure. Order don't matter. All right. So check this out. So this is graphing combined vertical and horizontal shifts, right? So given I have f of x is equal to the absolute value of x, we want to sketch the graph of h of x, which is going to be f of x plus 1 minus 3, right? So tell me what's happening in this graph real quick.
Take it forward.
It's going to go to the left. How many units? Okay, and then what else? Down 3 units. That's it. All right. So again, I'm really bad at art, so I apologize for this. I'm just trying over here. So this is supposed to be the absolute value of x, right? This is f of x equals the absolute value of x. I know them lines ain't straight. I'm trying. I'm trying over here, right? So you know what? I'm gonna do it on the same one, but hold on. I'm gonna pick another color. What's another color? I'm gonna do the blue. I'm gonna do the blue. All right. So for the h of x now, right? I'm gonna be shifting it 1 unit to the left, right? And then down 3 units, right? So I'm gonna come over here, 1 unit to the left, and then down 3. 1, 2, 3. Boom. There it goes. That's my h of x is equal to f of x plus 3 minus 3. All right. And if you wanted a point, like this point here would be 0, 0. Go ahead. It should be plus 1. Whoops. You're right. Thank you. All right. This one over here, this point I'm talking about right here, what is that? That's -1, comma, -3. All right. So that shows you the shift. 1 over to the left, down 3. All right. Questions? Make sense? Okay. Your homework is all of this kind of stuff. Like, is it shifted to the left? Is it shifted to the right? That's it? Okay, boom. How much is it shifted? Boom, boom. And in each question, they tell you the answer, so you don't gotta stress. All right. And you have unlimited attempts, and I really don't care how many times you try it. You do not get penalized for trying. All right. I don't know. Anybody computer science major in here? You are? Nice. Awesome.
I thought like this,
Yeah.
and see how we chase the formula right there, and kind of look what it's, you like, because I was gonna study the program, you can see that as like, let's say like, you know, if you wanna have a baby, she's pulling you away. You said, oh, like, you know, Once the cabinet out of control, move to the side. This is the math you use to be able to move to the sides.
Mm-hmm.
That's how I started thinking, like, what's the application of this type of thing? It's the
True.
process of-
True.
like, it's close. This time, you programs, but not, this time, it was big. Yeah, that's how I see it now.
Keep it 100 with you. When it comes to coding though, this is one of my least favorite things in coding. Yeah. Like the graphics, like that's not my thing. Math now. I like my math, you know.
Appreciate this,
Yeah.
Yeah. So that, yeah, it's from also because. There's a lot of things I love about information systems,
Yeah.
but when it comes to web design specifically. I like the seriousness of it, like, specifically like web design and program design. Like, I have like, I have USB converting something like that around the basis of visual logic framework.
Yeah.
So basically putting out operations.
Yeah.
You're creating, software.
Yeah.
It just gets tedious, I mean.
I feel you.
Brackets and, each bracket means something different. I think it's real tedious, I was just. That's why I started with Python. I was just trying to get.
Yeah. Graphics is the hardest part. I swear.
Yeah.
Yeah, you guys try.
So I guess somebody else calls that. It's the code, it gets a paragraph, what you should have.
Try that out. That one. You know what? I just remember you now. OMG. This whole time I'm looking at your face. Oh, but where do I remember? So for those of you that say y'all doing electrical engineering, y'all like want to do like electrical engineering, or y'all want to do like computer engineering? All right.
Basis skills, like after this, I'm going to get an expert.
Yeah.
So I'm gonna basically program this.
Okay. That's pretty cool.
I got like, on that way around the next two.
Yeah.
Or something like that.
Got you.
Right.
That sounds fun.
I'm not, good for.
Yeah. I mean, ain't nothing wrong with yeah. Nothing wrong with starting your own business and stuff like that.
At this class, I probably get a 4.
Yeah.
So I think I can do it, I can,
Yeah.
I get everything that.
And you Gucci, that's most of your grade. You know? Yeah. Yeah,
You know, that people said, I shouldn't give.
yeah,
Hey, it's possible, you know, what's about somebody that was there, you know, like, you know,
right, it's true.
like, it's
Yeah, true, true, true.
things like that.
Yeah. All right, y'all finish this? All right, bet. Talk to me real quick. What's happening in this?
I guess, you know,
Hmm.
but where's it at?
Hmm. So original graph is going to be. Oh, that was not a smart idea about this. Something like that, right? This is f of x is equal to the absolute value of x, right? And talk to me about h of x. What does that look like? Okay, up four, and then I'm moving to the left or to the right? To the right. All right. So
That's funny.
yeah, 1, 2, 3, 4. When we square it, what do you mean? So,
I go next time square.
mm-mm. Always from the general formula. So that's our graph right here. This is the h of x. All right. So just to recap, right? You know what? That's not a smart idea. Let's do how about pink. This is the origin right here. This is 0, 0. This point over here is gonna be. I'm gonna do it up here. That point is gonna be 2, 4. All right. Make sense? The +4 shifted the graph up 4 units, right? And then we have x minus 2, which is going to shift it to the right 2 units. Oops. All right, just for fun, just for fun, just for fun. All right. Let's answer this question. It says write a formula for a transformation of a toolkit reciprocal function. So f of x is equal to 1 over x. That shifts the function's graph 1 unit to the right and 1 unit up. Give me that equation real quick. Give me that equation. So let me write down the original. I have f of x is equal to 1 over x, right? What's that g of x going to be? Now let's recap, right? Wrong thing. Let's recap, right? I want to shift the function graph up or 1 unit to the right and then 1 unit up. So what we think?
X. What, X plus one. What?
I give you that. What else? Mhm. So 1 over x minus 1. Very good. And that's it.
I don't,
Nah, just that part. Yeah.
oh,
Because
that's,
right. Because one of them is affecting the y and the other one is affecting the x. That's why. All right. Question on it? Anybody? Go ahead. You don't get it? Which part you didn't get? Huh? Yeah.
What you just did right now makes, like, there's an environment stuff that I feel less.
Yeah.
But it's just being, it's just gonna be.
That's good. I appreciate it. Appreciate it. Yeah. Oh, because that's what they gave me. I'm just copying what they gave me.
Yeah, okay.
Yeah.
That's still the, that's still had something.
Mhm. Yeah. One to the right is like you're subtracting one from the x, so x minus one. And then one up is just adding one. I got you. Yeah.
Okay, so like, so do the same thing, so let's say like one of the X is like, 106.
Yeah.
The most calculation now, I go X minus one, so now it's not 106, now it's 105.
Mm.
And you know, 5 is less than 6, so it is 10.
I mean, I don't know if this helps, but you know that this is f of x is equal to 1 over x, right? And then you know if I'm shifting it to the right, you know that's going to be f of x, what, minus 1. So, you know, I would just plug in that. This becomes 1 over x minus 1. I don't know if that helps. Same idea. Yeah.
The
All right.
changes applies to X.
Yeah.
So, if like I got like over 1, it's only a defined number. But we only changing X, that's what we can change.
Right. All right. Give me 1 second. Let's answer a quick question. Be right back. But let that sink in. It's the idea. Vertical. It's transformation, Skippy. Okay. We got more to talk about with transformations. Not gonna lie, this is a heavy topic. So now we're gonna talk about graphing functions using reflections about the axes. It's a whole nother thing right here. All right. So another transformation that can be applied to a function is a reflection over the x or the y axis. A vertical reflection reflects a graph vertically over the x axis, right? While a horizontal reflection reflects the graph horizontally across the y axis. So for example, right? Our dark blue line here, that's our original function, right? If we're reflecting it about the x-axis, right? You see the x-axis, the horizontal axis right here, right? I'm taking that graph and it's like I'm flipping it upside down on the bottom, right? So that's how I get this turquoise line right here. That's the vertical reflection, all right? For a horizontal reflection, again, I'm back to my dark blue line. That's my original function, right? I'm gonna flip that over the y-axis. So it's like I'm taking it from one side, just turning it around onto the y-axis, right? So that's how I get this orange line, which is my horizontal reflection. All right. Questions about this? Mhm. So vertical reflection, I'm flipping it over the x-axis. So I take my original, that's like I flip it downwards, right? Horizontal reflection, I take my original and I flip it around, right, to the other side. All right. Now I'm gonna get into the nitty-gritty of how you actually do it, like using a chart, but this is the idea behind it. So notice that the vertical reflection produces a new graph that is a mirror image of the base or the original graph about the x-axis. The horizontal reflection produces a new graph that is a mirror image of the base or the original graph about the y-axis. All right. Make a special note about that. Just want to hammer the idea home real quick. Reflections. All right. So given a function f of x, a new function g of x is equal to negative f of x is a vertical reflection of the function f of x, sometimes called a reflection about or over or through the x-axis. All right. Given a function f of x, a new function g of x is equal to f of negative x. This is a horizontal reflection of the function f of x, sometimes called a reflection about the y-axis. Okay? It's a little challenging, so let me give you a little bit of tea before we continue. All right? So given a function, reflect the graph both vertically and horizontally, right? So here's how we do it. Step one, you multiply all the outputs, y value, by -1 for a vertical reflection, right? That's how you do a vertical reflection. The new graph is a reflection of the original graph about the x-axis, right? All right. So step two, right? We multiply all the inputs, the x's, by -1 for a horizontal reflection. The new graph is a reflection of the original graph about the y-axis. All right. So one of them I'm multiplying -1 times the original function. That's how I get the reflection over the x-axis. The other one I'm multiplying -1 by the input. That's how I get the reflection on the y-axis.
I would say, you know, before, but,
A little different because it's not changing now. It is changing, but it's not changing. Like it's not shifting, it's reflecting. Yeah, flipping. That's a good word. Yeah,
the first one, so,
yeah,
vertical,
yeah.
but it's shaded the,
Right.
seven, so it's not saying X now a negative that, so if it's six here.
Right.
Now it's six, positive six, now it's -6.
Right. So like the first one is like they were like sliding. But this is not sliding. This is like flipping a little bit different. All right, let's check this out. So reflecting a tabular function table, right? Horizontally and vertically, right? So a function f of x is given as a table. There you go, right? So now we want to do these two things. You want to do g of x, right? Which is going to be equal to negative of f of x, and h of x, which is going to be equal to f of negative x, right? It's as simple as it is, as you see it here, right? You got your x, you got your f of x, right? G of x is literally negative f of x. It's literally that, right? Just put a line right here. So that being said, what am I going to write here? -1. What am I going to write here? Very good. Next one. Very good. Next one. Perfect. All right. H of X is literally what you see right there, right? This is f of negative x, right? So what am I going to write here? -2. Mm-hmm. Mm-hmm. Hold on one second. Damn pop-ups. Hold on one second. It's not looking so hot over here. Let's try this again. Hold on. We have the x's here. I'm gonna just make a separate table for this. 2, 4, 6, and 8, right? And then what's happening, right, for h of x, these are all going to turn negative. -2, -4, -6, -8, right? So what is the y going to be? It's going to be the same, right? The same as the f of x. So that's going to be 1, 3, 7, and 11. And that's the shift for you. All right. So the g of x has the same input as the x up top here. Matter of fact, let me just write that in so it just looks nicer. Right? So the g of x has the same input, but for the h of x, which is f of negative x, the x has changed negative, but the y value stayed the same. Right? That's it. Questions on it? Sure. Like you want to see the words for this? Oh, go ahead. Yeah, I got you. I got you. No worries. The what? The graph. This one you mean? Okay. Got you. All right. That's all good. I got you. No problem. No problem. All right. That being said, you guys try. Like looking out each of the windows, and I'm like, it was looking mighty dark outside. shade. What's the shade? Yeah, as long as it ain't rain. I mean, it's been hot though, so I'll take a little bit of rain, but like if it wants to rain right now and then stop by the time class ends, I'm down for that, you know. Yeah, yeah,
I like at the game out to some shop.
yeah, yeah. I
I
like, right? Yeah, I saw that online. That was hilarious. Mhm. But could the palm tree survive here?
Yeah,
It could.
they can get them.
Okay.
They can last. I still feel like the sun too.
Yeah. Yeah.
Yeah, it's all affected by those. So like,
Yeah.
wait,
Yeah. True. True. Last. Nah, was it last winter or the winter before that? Like when we went like a year and change without snow. Like that was crazy. Yeah. Yeah. Yo, it was so long that I thought that snow wasn't gonna come back. You know? I was trying to picture myself at like age 80, be like, yo, back in my day, snow used to fall. We used to have this thing called a white Christmas. Right? Yeah. Yeah. Hell yeah. Yeah. Yeah, man. Now yeah, it's true. Now you remember when Bloomberg was mayor? It'd be like 3 feet of snow outside and be like, yeah, school's still open. You'd be watching the news in the morning, like hoping to see your school's name, and it's like, nope. No, that's another state. All right, let's take a look at this real quick. So, ba, 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 ba. I'm just gonna copy what I have. -2, 0, 2, 4, 5, 10, 15, 20. All right. For the g of x, what's changing? The x or the y? So I'm looking up here. It's the y that's changing, right? So I'm putting all the negatives right here. Bam, bam, bam. So everybody got, right? Awesome. All right, let's check it out. Let's check out the h of x real quick. Doo, doo, doo. Again, I'm just copying down what I have real quick. So I have -2, 0, 2, 4. This time I want the h of x. I have 5, 10, 15, 20. Let me scroll up real quick. For the h of x, right? I'm looking right here. What's changing, the x or the y? The x, right? So it's going to be positive, negative, negative, negative. You know, there's no such thing as -0. All right. Everybody got that? Yeah. Mm-hmm. Yeah. Mm-hmm. It's flipping them. Yeah. Yeah. Got you. Questions on this? Make sense? All right, let's keep going. So next thing I want to talk about, even and odd functions. All right. So some functions exhibit symmetry so that reflections result in the original graph. For example, horizontally reflecting the toolkit functions f of x equals x squared and f of x equals the absolute value of x will result in the original graph, right? So you remember when we had the parabola? If I reflected about the y-axis, it's the same thing. It didn't change nothing, right? Remember the absolute value like a v? If I reflect that about the y-axis, it's the same thing. It didn't change nothing, right? So that's what they mean right here. We say that these types of graphs are symmetric about the y-axis. All right. Functions whose graphs are symmetric about the y-axis are called even functions. Right. So what did we learn now? X squared, quadratic formula, absolute value of x is an even function. Right. Those are even functions. Okay. If the graphs of f of x equals x cubed or f of x is equal to 1 over x were reflected over both axes, right? So reflected about the y and then over the x kind of thing, right? The result would be the original graph as shown. So let me show y'all that real quick. So let's start off with A, right? I have f of x is equal to x cubed. There you go, right? Now, let's say that I first I reflected about the y-axis, right? So, boom, that's how it goes. So I'm flipping it around, right? Now, after I flip it around, let me reflect it about the x-axis. So now I'm flipping it up. I'm right back to the original equation where I started at, all right? So the cubic toolkit function, right? B is a horizontal reflection of the cubic toolkit function, excuse me. Horizontal and vertical reflections reproduce the original cubic function. All right. What does that mean? I'll tell y'all right now. So we say that these graphs are symmetric about the origin, right? So a function with a graph that is symmetric about the origin is called an odd function. All right. Special note. A function can be neither even nor odd if it does not exhibit either symmetry. All right. For example, f of x equals 2 to the x power, right? Is neither even nor odd. Also, the only function that is both even and odd at the exact same time is the constant function f of x is equal to 0. All right. Giving y'all the T, giving y'all the T real quick. Let me drop a definition on y'all real quick. So even and odd functions, right? So a function is called an even function if for every input of x, f of x is equal to f of negative x. So if I plug in negative x and I get back the original function, it's an even function. Done, right? The graph of an even function is symmetric about the y-axis. All right. The graph of an even function is symmetric about the y-axis. A function is called an odd function if for every input of x, f of x is equal to negative f of negative x. So if I reflect it over the x-axis and the y-axis in either order, doesn't matter, right? And I get back to the original function, that's an odd function right there, right? The graph of an odd function is symmetric about the origin, all right?
What makes it odd is that, pretty much that they're both touching at that origin point.
Not that they're touching. If I reflect it, like flip it over to y, flip it over to x, and I get back to the original question where I started at, then it's an odd function. Yeah. We're gonna see an example. But real quick, let me give y'all a little T real quick. All right. So given the formula for a function, determine if the function is either even, odd, or neither. Here's how we do it. Step one, determine whether the function satisfies f of x is equal to f of negative x. If it does, then it's even. So when I plug in negative x, if I get back out the original function, that's an even function. I'm done, right? Determine whether the function satisfies f of x equals negative f of negative x, right? And if it does, it's odd. So if I plug in negative x and then I multiply the whole equation again by -1, and I get back to the original, that's an odd function right there. All right. If the function does not satisfy either rule, right? That's neither an even nor odd function right there. Right?
pretty much said that we got here first.
Right.
I see how to move back when it's the equation.
Exactly. All right. I promise you, it's real easy. I promise you. Check this example out. Check this example out. So we want to determine if whether a function is even, odd, or neither, right? So is this function, which is f of x equals x cubed plus 2x, is it even, odd, or neither? Let's test it to see if it's even, right? So to test if it's even, what am I going to plug into it? Negative x, right? So let me plug in the negative x and see what happens. All right. My fault. So I'm plugging in negative x real quick, right? So let me see what happens when I do that. I do the math on it. What does this become? This becomes negative x cubed minus 2x, right? Is that the same thing as the original? No. All right. Let's go one step further. Let's go one step further. So now I want to do negative, oh shoot, of the f of negative x. So essentially, what am I doing, right? I'm gonna multiply this other function over here by -1. Right, like -1. Let me just distributing this. That's all I'm doing, right? And now when I'm done distributing this, right, this becomes x cubed plus 2x. Is that the same thing as the original? It is. So what is this? Is it even, odd, or neither? Odd. That's it. I'm done. Easy? Go ahead.
All three of the steps here.
Or neither. Right. Yeah. So I know you might say like, oh, it just failed the even thing, so that means it's odd. You know, I know the temptation is there to just say that, but if it's a neither situation, like you have to verify that, you know, by going one step further to multiply the whole thing by -1 to see if it brings you back to the original question. You know, that's the way you tell if it's neither. All right. So right after we verify, right after we verify that it's not even, that it's odd. No, let me say that again. Right after we verify that it's not even, right? We multiply the whole thing by -1 to verify if it's odd, right? If it comes back to the original function that we started off with, it's odd. But if it doesn't, if it's something completely brand new, that's neither even nor odd. Right?
Or we get a whole other.
A whole nother equation. Yeah. It wouldn't match. Mhm. Hmm? All right. This is dangerous, but I'll make up something. Go ahead.
When he goes back after this third step.
Mhm.
To where it was originally,
It's odd.
but would it be if it's even?
So let's look at that. Um, what's a good letter in the alphabet? Huh? What was it? G. All right. Let's say that G of X is equal to 2 to the X power. I don't know. I'm just making it up. Right? All right. So I want to test if this thing is going to be even. So g of negative x, this is going to be 2 to the negative x power, which becomes what? 1 over 2 to the x, right? Is that what I started with? Nah, that's not. So I know it's not even. All right. Let's go a step further. All right. So I want to do negative of g of negative x, right? So I'm multiplying the whole thing by -1. So this is going to be -1 over 2 to the x. Is that the original? This is neither. How you spell neither? Neither? Something like that. I don't know. In fifth grade, I got kicked out the spelling bee, and after that, I couldn't spell. Yeah, it would match. Yeah. Yeah. It'd come right back to where it was. Right. That's what I want to know. Is it even, odd, or neither? Right. I plug in negative x to see if it's even. Yeah. You take the answer from the even, and then you multiply that whole thing by -1 to verify if it's odd. Right? And if it don't work, you already know it's neither. Yeah. Yeah.
Like the breakdown of where from the, we didn't honor neither, but we did the-
When it's even,
Neither.
what happened?
Even.
Which one?
But I don't. They go in X years. It's even, right?
No, it was odd. This one.
Not the second one. It's the same one as the original one.
With the x cubed?
Yes, that's right.
That's odd. Yeah, that's odd. And then the purple was neither. Um, Let me get another letter out the alphabet. H. All right. So h of x, let's say, is equal to x squared, right? So then I want to check to see if it's even. So this is h of negative x. So when I plug in negative x here and I square it, that comes back out to still be x squared. That's even. Right? Yeah. Yeah. But it didn't match the original. That's the issue. See, look. Yeah.
So, but if you put that negative,
Yeah.
like outside and do parentheses.
Right.
It will be even.
No,
Or
no.
we don't.
No, we have to plug in the x as negative, yeah. Because see, when we plugged it in here, it changed the whole thing. It didn't match the original. That's the trick. Yeah. You're welcome. I just want to make a special note real quick before we move on. All right. So consider the graph of f in this figure right here, right? Notice that the graph is symmetric about the origin, right? So for every point x comma y on the graph, the corresponding point -x -y is also on the graph. So for example, I have this point right here, 1 comma 3, right? The corresponding point -1 -3 is also on the graph. That's symmetry over the origin. All right. So just want to show y'all that. Help me out real quick. Even, odd, or neither? Which one? Good. Why?
Squares. Square towards.
Oh,
Build.
okay, good guess. All right.
I said,
Mhm.
yeah, change.
Well, you could plug in what to prove that it's even. Negative s, right? So f of negative s would give me what? Negative s to the fourth plus 3 times negative s squared plus 7, right? This is going to be still s to the fourth plus 3 s squared plus 7. So this is even. All right. Questions on that, anybody? Good? All right. All right. Let's take it up a notch. So we're going to talk about graphing functions using stretches and compressions, right? So adding a constant to the inputs or outputs of a function changed the position of the graph with respect to the axes, but it did not affect the shape of the graph. We now explore the effects of multiplying the inputs or outputs by some quantity, right? So we can transform the inside input values of a function, or we can transform the outside output values of a function. Each change has a specific effect that can be seen graphically. Okay. So here we go. So we're talking about vertical stretches and compressions, right? So when we multiply a function by a positive constant, we get a function whose graph is stretched or compressed, right? Vertically, right? In relation to the graph of the original function. If the constant that's being multiplied that by it, right, is greater than 1, we get a vertical stretch, right? If the constant is between 0 and 1, a fraction, right? We get a compression, right? Vertical compression, right? And then the figure shows you what happens when you multiply 2 and 0.5, right? So f of x, the blue line, the dark blue line, that's my original function, right? If I multiply it by 2, which is a constant number that's bigger than 1, I'm stretching my graph up, right? This is vertical stretch, right? Hey, okay. So if I multiply, right, my function by 0.5, right, I'm compressing, right, my function right there, right? So that's a vertical compression. All right. You give y'all a little definition real quick before we jump on into anything else. All right. Vertical stretches and compressions. Given a function f of x, a new function g of x is equal to a times f of x, where a is a constant, right? It is a vertical stretch or vertical compression of the function f of x, right? So if a, the number that we're multiplying it by, is greater than 1, the graph is stretched, right? If a is between 0 and 1, the graph will be compressed. All right. And then if A is less than 0, it will either be stretched or compressed, but it would also be a reflection, a vertical reflection. So over the y-axis, right? So that's that.
And affects both, y and z axis.
No. The A only affects the y. Yeah. Hmm. It's either stretching it or compressing it. So So real quick, give y'all a little bit of tea. All right. So given a function, you want to graph its vertical stretch, right? Here's how you do it. Step one, identify the value of A, all right? Multiply all the ranges. Range is another word for the Y values, right? So multiply all the ranges by the value of A, right? So if A is greater than 1, the graph is stretched by a factor of A. If A is between 0 and 1, the graph is compressed by a factor of A, right? And if A is less than 0, then you already know it's going to be either a stretch or a compression, but it's also going to be a reflection over the Y-axis, right? X-axis, excuse me.
Well, being on the X-axis question.
Right.
Okay.
Exactly, yeah. Yeah. All right. So given a table function, right, and assuming that the transformation is a vertical stretch or compression, right, you want to create a table for vertical compression. This is how you do it, right? First, you want to determine the value of A, and then you want to multiply all of the output values by A. That's it. All right, check this out, check this out, check this out. So finding a vertical compression of a table function right here, right? So we have this table and we want to create a table function g of x where we have 1/2 times f of x, right? We're compressing it, right? We're compressing it. All right. When I compress it, does the x values change? No. All right. So I got the same x values. So I got 2, 4, 6, and I got 8, right? But what is changing for g of x? The y values, right? So this is going to be 1 times 1/2. Let's call that 1/2. This is going to be 3 times, I should have put on the other side, but whatever. Times 1/2, this is 3/2. This is going to be 7 times 1/2. Call that 7/2. And this one's going to be 11 times 1/2. Call that 11/2. Uh-huh. I'm sorry? Which one's 1? Yeah. 1 times 1/2 is what? Yeah. Just multiplying them, that's all. Yeah. So this graph is squished. All right. Questions on it? Good? Hmm. Yeah. Promise you it won't be that bad. Maybe Wednesday. Yeah. I feel like I might need to actually like go through material on Tuesday. Just want to make a real quick special note. All right. So the result is that the function g of x has been compressed vertically by 1/2. So each output value is divided in half. So the graph is half of the original height. All right. That's what happened. You guys try. All right. Tell me what to write. Let's see what you got for the X's. Good. What you got for the G of X now? Okay. 9, 12, 15, 0. Okay. I'll take it. I'm trusting y'all on the math now. All right. Questions on this though? Anybody? Good? All right. Mhm. Right. This would be a compression. Yeah. All right. So horizontal stretches and compressions now. We just spoke about vertical. Let's talk about horizontal stretches and compressions now. So now we consider changes to the inside of a function. So when we multiply a function's input by a positive constant, we get a function whose graph is stretched or compressed horizontally in relation to the graph of the original function. So if the constant is between 0 and 1, we get a horizontal stretch, right? So when it's a fraction, we get a horizontal stretch, right? Now, if the constant is greater than 1, then we get a horizontal compression, right, of the function. It's okay. I just want to like just jump to a graph real quick. All right. So there we got this graph right here, right? Y equals x squared is a dark blue line. That's the original that I'm talking about right here, right? That's the original. Now, notice if I multiply it, right, by a fraction, right? So 0.5 is like 1 over 2. The inside, I'm multiplying it by a fraction. I'm horizontally stretching it out, right, by the fraction. But when I multiply it by a constant number that's bigger than 1, like 2, right, I'm compressing it, right, by 2. All right. So that's what this is essentially saying.
So,
It does. It's a backwards idea, but it's true, you know.
I don't know if it's sitting the first. For some sort of-
Right.
Uh,
Yeah. Go ahead.
Well, by the-
Go ahead. You want the words?
Just,
Just the graph?
yeah, just a graph.
All right. All right.
first.
Yeah. All right. I got you. I'll give you the words. Listen. Yeah. All right. Here you go. Here go the words right here. You're welcome. All right, so given a function y equals f of x, right? The form y equals f of bx results in a horizontal stretch or compression. Consider the function y equals x squared, right? We observed from this previous picture right here, right? The graph of y equals 0.5x squared is a horizontal stretch of the graph of the function y equals x squared by a factor of 2. The graph of y equals 2x is a horizontal compression of the graph, right? Of the function y equals x squared by a factor of half. All right. A little bit of a reverse. Give y'all a little bit of definition real quick. So horizontal stretches and compression. So given a function f of x, a new function g of x equal to f of bx, where b is a constant, is a horizontal stretch or horizontal compression of a function, right? If, let's say, b is greater than 1, then the graph will be compressed by b, right? So compressed by b. If b is between 0 and 1, so like a fraction or a decimal, it's going to be stretched by a factor of 1 over b. All right. Let's say b is less than 0, though, right? So it's negative now, right? It could be either a stretch or a compression, right? But it's going to be a reflection over the horizontal axis. All right. So the reverse now.
I heard that one. It looks like so much we multiply the x-axis. So if you give me 2, if b is 2, and I was 4.
I'm multiplying it on the x, not the y. Yeah, yeah,
If I was 2, down 4,
right.
that's make it bigger.
If you were 2 and now you're 4, you're up. So you've been compressed. You moved up. You didn't move this way, you moved this way.
But I can't do the x-axis. X-axis always up the bottom.
It is kind of, yeah.
That's what I mean, like, and now it's b times x. And let's say I do x, 2 times 2, now it's 4. So if I was at 2 coordinates, and now I'm at 4, getting bigger.
If you were,
That's
I'm trying to think, like if you were at 2, like I'm thinking of y equals x squared, right? So if x was 2, the y component would be 4, right? But if it was compressed by 2, right? So like 2x, for example, right? That would be 2 times 2, 4, and 4 squared would give me 16, you know? So
16 is all the way down.
nah, 16 is up there. That's the y. Yeah. Yeah.
Yes.
Yeah. Yeah. You're compressing. Yeah.
Then you're slower, you're going up.
Right.
Maybe that's still on the table.
It'll make more sense then. Yeah. Real quick, let me give you a little bit of tea before we jump to the table. All right. So given a description of a function, sketch a horizontal compression or stretch. So what we want to do is first write a formula to represent the function. We want to set g of x equal to f of b of x, where b is greater than 1 for compression or between 0 and 1 for stretch. All right. So let's look at the table. So you want to find a horizontal stretch for a tabular function, right? A function f of x is given by the table. We want to create a table of the function g of x, which is equal to f of 1/2 times x, right? So this is going to be a stretch, all right? What's changing here? The x, right? So all right. So let's say I have 2, 1, 4, 3, 6, 7, 8, 11. We said the x was changing, right? So we're gonna multiply this by half, get out 1, by half, get out 2, by half, get out 3, by half, we get out 4. All right. So that's our stretch. Questions on this? We good?
It's not,
Yeah.
I just think,
Yeah.
but even that, it's still, there's still a question at the end.
Where's the bottom?
Divided it by 2, yeah. I mean, multiplying by a fraction, dividing the same thing. Yeah. Yeah.
I'm like, one change, I'm like, oh, I mean, that's asking. It's technically, I get like, yeah, you know, second half of my thing.
Mm-hmm. Let me see. It's not really clear in the graph, but this is kind of what happened with those points. Whereas like in A, that was the original with the f of x, and then this is the g of x. Kind of hard to see. You know, it got not shifted, stretched is the word I'm trying to say, you know?
I should look at that.
No, on the y. This was the horizontal stretch. Yeah, yeah.
The thing was just like, hey, it's not here, and it's,
Yeah.
I'm getting,
And it changed by a factor of 2. So special note, because each input value had been doubled, the result is that the function g of x has been stretched horizontally by a factor of 2. All right? Okay. All right, last thing for tonight.
like, excited, so technically stressing that time.
The x's is what's stretching, you know? Like before, it was like before I was able to get to the y value by just it being 1, but now I have to like go to 2 just to get to that same y value. That's the stretching that's going on. Oh. All right, little story real quick, right? So until the 1920s, the so-called spiral nebula were believed to be clouds of dust and gas in our own galaxy, some tens of thousands of light years away. Then astronomer Edwin Hubble proved that these objects are galaxies in their own right at distances of millions of light years. Today, astronomers can detect galaxies that are billions of light years away. Distances in the universe can be measured in all directions. As such, it is useful to consider distance as an absolute value function. In this section, we're going to investigate absolute value functions. That's the last thing we're talking about today. Okay? So let's explore this a little bit, understanding absolute value. All right. So recall that in its basic form, f of x is equal to the absolute value of x. The absolute value function is one of our toolkit functions. The absolute value function is commonly thought of as providing the distance the number is from 0 on a number line. Algebraically, for whatever the input value is, the output is the value without regard to the sign. All right? So that's how I remember absolute value. It's the distance that a number is from zero. All right? Let's go a step further, all right? So absolute value function, all right? So the absolute value function can be defined as a piecewise function. So f of x is equal to the absolute value of x is going to be x if x is greater than or equal to 0, or negative x if x is less than 0. All right? Let's check out this example. So here we want to determine a number within a prescribed distance. So describe all the values of x within or including a distance of 4 from the number 5. Right? This sounds a little crazy, but here's what I'm saying. Here's what I'm saying. Right? Let's say I had a number line. And in the middle, I'm starting at 5, right? What I want to know is what is 4 units to the right? What is 4 units to the left? All right. Tell me what they are real quick. 1 and 9, right? So I have 1, 2, 3, 4. So this would be 6, 7, 8, 9. And then I have 1, 2, 3, 4. This would be 4, 3, 2, 1. Right? So all the numbers, right? I'm gonna say x is gonna be 1 less than x less than 9, right? Because in between 1 and 9. Right? That's what this means. Right? But let's say I want to say this with like an absolute value kind of thing, right? What I'm saying is if I took the absolute value of, let's say, x minus 5, right? And then I would say that that is equal to 4 to give it 4 units to the left or right. This is another way of representing this part here, right? From 1 to 9. Questions on that? Let me just modify this a little bit. Less than or equal to 4. Now it looks a little bit better. All right. Yeah. Because if I said equal, then it's just one number. It should have been the absolute value to include all of them. That's my mistake. All right. Just make a special note real quick. So I want to note that for -4 less than or equal to x minus 5, right? We can solve for x, just add 5 to both sides. It's going to give us 1 is less than or equal to x. And then for x minus 5 less than or equal to +4, right? We can add 5 to both sides. That will give me x is less than or equal to 9, right? Put them together and we get back to our original part that we had before. 1 less than or equal to x less than or equal to 9, right? So the absolute value of x minus 5 is less than or equal to 4, right? So generally in math, we like to use the absolute value function as opposed to doing the inequality. Okay. So how about this one? We want to describe all the values of x between a distance of 3 from the number 2. All right. So same idea. I want to get a number line going. I'm starting off at my number 2. I want 3 units to the left, 3 units to the right. So 1, 2, 3, 1, 2, 3. What am I gonna write here? Tell me. Not -1. Oh, wait, yeah, you're right. You're right. I'm sorry. -1, 0, 1. What's the other side? 3, 4, 5. Good. Very good, right? So now we know that this is going to be what? -1 less than or equal to x less than or equal to 5. I want to make this a little bit nicer, right? Use an absolute value function, right? So what would I say? I could say x, absolute value x, what?
Right. So,
3 less than or equal to
let's see.
2. Okay. Sounds good. All right. If we were going to solve this, we would have x minus 3, let's say less than or equal to 2, and x minus 3 less than or equal to -2. Solve for x in both, right? I'm going to add 3 here, add 3 here. So this is x less than or equal to 5, right? That's right. Over here, I'm going to add 3 here, add 3 here. So this is x less than or equal to +1. 2, 1, 0. That didn't work out right there. What did we do wrong here? Hold on.
Negative.
Which one's -3? Nah, that's right. I'm adding 3 to both sides.
That's the value.
Also, another thing too, this should have been, I think, flipped around. This should have been greater than or equal to. Yeah. And this is flipped around too. Why isn't that -1? That should have been -1. Let me think about that. 1 second. Uh-huh. You know, you know what it was? We had to switch this around. This is the 2 and this is the 3. That's why. Outside of the what? Mm-hmm.
We're changing the value of 3 outside of the value.
Right. And the reason for that is because of the absolute value, right? Remember, absolute value, like, how can I say this now? I'm gonna come back to this in 1 second. Come back to this in 1 second. Let's say that I had the absolute value of x, right? And let's say that it was equal to, I don't know, 5 is coming to mind, right? If I take the absolute value of 5, that equals 5. But if I take the absolute value of -5, that also equals 5, right? So I have to account for both of those situations. That, yeah. Uh-huh.
This side. Instead of adding negative, you're changing the sign from inside of the brackets. You're changing it on the outside.
Yeah, on the outside. That's what's getting changed. So let's try it now. Let's try it now. Add 2 here. Add 2 here. This is x less than or equal to 5. Good. Add 2 here. Add 2 here. Now we got it. X greater than or greater than or equal to -1. All right. So what did we learn from that, right? The number that you're starting at is the one that's next to the x, right? And then the one that's going the distance is the one that's on the outside, right? However many units we're moving from. All right. Mhm.
But I mean, it's but that they not much more minus.
Yeah,
Kind of.
yeah. The x is radical.
But now they like,
Yeah,
that's not a,
that's the thing. Yeah,
right,
right. Yeah.
but it is that.
Mm-hmm. It is that. Mm-hmm.
So,
All right, let's keep it moving. Let's keep it moving. We got time going. Let's try another one real quick before we jump into some other stuff. So this is another example, right? It says students who score within 20 points of 80 will pass a test, right? What write this as a distance from 80 using absolute value notation, right? So tell me what to write. This is gonna be X what? All right. So minus 80 less than or equal to. Okay. And that's it. All right. Mm-hmm.
the change quantity that I haven't go to the outside.
Right.
The original value that we begin with.
Right. Mm-hmm. That's it. All right, let's take it up a notch. So we're going to be solving an absolute value equation. So now that we can graph an absolute value function, we will learn how to solve an absolute value equation. To solve an equation such as 8 is equal to the absolute value of 2x minus 6, we notice that the absolute value will be equal to 8 if the quantity inside the absolute value is 8 or -8, right? This leads to two different equations that we can solve independently. So we have 2x minus 6 equals 8, or we have 2x minus 6 equals -8. Little math, boom, boom, boom. We get x is equal to 7, x equals -1. Knowing how to solve problems involving absolute value functions is useful. For example, we may need to identify numbers or points on a line that are at a specified distance from a given reference point. An absolute value equation is an equation in which the unknown variable appears in absolute value bars. So, for example, absolute value of x is equal to 4, or absolute value of 2x minus 1 is equal to 3, or absolute value of 5x plus 2 minus 4 is equal to 9. Okay? So now we want to talk about how to solve those. Just so we clear though, right? Solutions to the absolute value of equations. All right. So for real numbers a and b, an equation of the form the absolute value of a is equal to b with b greater than or equal to 0 will have solutions when a is equal to b or when a is equal to -b. If b is less than 0, the equation absolute value of a is equal to b will have no solution. All right. So that's that. Reason being, you can't have a negative answer for an absolute value. Simple as that. All right. All right. So given the formula for an absolute value function, find the horizontal intercepts of its graph. What we want to do is first isolate the absolute value term, right? You want to get that by itself. Then we want to use the absolute value of a is equal to b to write A equals B or negative A equals B, assuming that B is greater than 0, excuse me, and then you just want to solve for X. All right. So blah blah blah. One positive answer, one negative answer, solve for X, like we did before. And that's it. So for the function f of x is equal to the absolute value of 4x plus 1 minus 7, right? We want to solve for x in this situation, right? I'm going to have two things going on. One is going to be 4x plus 1. Yep, absolute value. Forget that. No, let me keep the absolute value. Minus 7. Set that equal to 0, right? Because that's the f of x equal to 0. Add 7 to both sides. So now I have absolute value of 4x plus 1 is equal to positive 7. I'm going to have two situations, right? One situation is going to be 4x plus 1 equals 7, and I want to solve for x. Another situation is 4x plus 1 is equal to negative 7. And then you just solve for x. Subtract 1, subtract 1. 4x equals 6. Divide by 4, divide by 4. X equals 3 over 2. Done. Right? Another one. Subtract 1, subtract 1. 4x equals negative 8. Divide by 4, divide by 4. X equals negative 2. All right? That's the other one. Questions on this? The beginning? So I was given f of x is equal to absolute value of 4x plus 1 minus 7. I'm going to set it equal to 0, as they did over here. So that gives me the absolute value of 4x plus 1 minus 7 equals 0. After that, I'm just like adding the 7 and kind of solve for it, And that's that.
Yeah, they always be E absolute.
I got you. I got you. Let me just say a couple more things, then we'll wrap up real quick. I got you. Real quick. Question and answer. So should we always expect two answers when solving the absolute value of A is equal to B? No, we may find 1, 2, or even no answer. So for example, right, there is no solution to 2 plus the absolute value of 3x minus 5 is equal to 1, right? How do I know that there's no solution here, right? If I subtract 2 from here, you know what I got to do to one side, I got to do to the other, right? So now I got absolute value of 3x minus 5 is equal to negative 1. But I can't get an absolute value of negative 1. That don't make sense. Done. There's no solution there. All right. Real quick, give you a little bit of tea. So given an absolute value equation, right? We want to solve it. First thing that you want to do is isolate the absolute value term. Use the absolute value of A is equal to B to write A equals B or A equals negative B, and then you want to solve for X. All right? That's how you solve the absolute value equation questions. Sure. You said down like this way? Okay. You're welcome. All right. Right. It has to equal to a positive number. If it not included. No. It just has to be a positive number, right? If it's negative, there's nothing you could do. It's just there's no solution to that. All right. 1 second. Spoke about that. All right, I got one more thing left to talk about just because of the homework. If y'all gotta go, I understand. Go, like it's gonna be on the recording, so you can just watch it. All right. But one last thing, I just want to talk about absolute value and inequalities, right? Because that's gonna be on the homework, and after that we can go. All right. So last topic, right? So solving an absolute value inequality, all right? So absolute value equations may not always involve equalities, right? Instead, we may need to solve an equation within a range of values. We would use an absolute value inequality to solve such an equation. Absolute value inequality is an equation of the form absolute value of A less than B, or absolute value of A less than or equal to B, or absolute value of A greater than B, or absolute value of A is greater than or equal to B, for example. Where an expression A and possibly, but not usually B, depends on a variable X. Solving the inequality, right, means finding the set of all X's that satisfies that equality. Usually, this set will be an interval or the union of two intervals. All right. So there are two basic approaches to solving absolute value inequalities: graphical and algebraic. The advantage of graphical approach is we can read the solution by interpreting the graphs of two functions. The advantage of the algebraic approach is it yields solutions that may be difficult to read from the graph, right? So for example, we know all the numbers within 200 units of zero may be expressed as the absolute value of X is less than 200, or negative 200 is less than X, which is less than 200. Suppose we want to know all the possible returns on an investment if we could earn some amount of money within 200 of $600. We can solve algebraically for the set of values X such that the distance between the X and the 600 is less than 200. We represent this distance between X and 600 as the absolute value of X minus 600. All right. It's just easier when we do it algebraically. So the absolute value of X minus 600 is less than 200, or negative 200 is less than X minus 600, which is less than 200, right? And then negative 200 plus 600, and we add 600 to all of them. X minus 600 plus 600 and 200 plus 600 will give us 400 is less than X, which is less than 800. This means our return would be between 400 and $800. Sometimes an absolute value inequality problem will be presented to us in terms of a shifted and or stretched or compressed absolute value function, where we must determine for which values of the input the function's output will be negative or positive. All right. So a little T. There's a little T on how to do this. So given an absolute value inequality of the form, absolute value of X minus A is less than or equal to B, for real numbers A and B, where B is positive, we want to solve the absolute value inequality algebraically. So first, step one, we want to find the boundary points by solving the absolute value of X minus A equal to B, right? Two, we want to test the interval created by the boundary points to determine where the absolute value of X minus A less than or equal to B is, right? And three, we want to write the interval or union of intervals satisfying the inequality in the interval, right? Inequality or set builder notation, right? So that's just how we're going to write our answers. All right. So let's take a look at one example just to see how we're going to write our answers, right? So solving an absolute value inequality. We want to solve the absolute value of x minus 5 is less than 4, right? So absolute value x minus 5 is less than 4. Remember, there's two situations going on here, right? One situation is going to be what? X minus 5 less than 4. And what's the other situation? Greater than -4, right? Right? And then you're just going to solve for it, right? So I'm going to add 5 here, add 5 here. This is going to be x less than, what's that, 9, I think. Add 5 here, add 5 here. What's this? X is greater than +1, right? So we could say this is 1, right? Less than x less than 9, for example, right? Or we could say, well, let me see, set builder notation, right? We could do from 1 to 9,
So,
you know?
pretty much when we get it with
Mm-hmm.
greater than or less than 8, greater than or less than 8, it's pretty
Mhm.
much like, now, you not only flip the number, flip the sign to.
Right.
Yes, right there.
Right. You know, another way to do this that might make it a little bit easier. Right. Another way to make this maybe a little bit easier. Like, I don't know if it's easier to look at it like this, right? You see how you have that absolute value of x minus 5 less than 4? If it was like this, -4 less than x minus 5 less than 4, I don't know if that helps. You know, when we're dividing, we switch the sign. But this is different though, because we're trying to solve for x. You know? So it's going to give us two answers. I don't know if this second part helps a little bit, you know, and then all you have to do is just kind of add 5, add 5, add 5, and then you get back to the 1 less than x less than 9. I don't know if that's easier. But yeah. Yeah, sure.
Funny question, just want to say something on the question,
Yeah.
because I wanted to see the,
Uh-huh.
basically, do you see how they decided was a switch?
The sign did get switched. You had the x minus 600, right? But then that's going to be within 200, so plus and minus 200. Yeah.
Okay, I get it.
Yeah.
Uh,
It might be easier just to do it out in this long line right here, right? Like where you just put the x minus 600 in the middle, and then you have the -200 and +200, and you just solve for both sides and call it a day. You know,
Yeah.
that might be the smarter way.
Like, that's
Yeah.
fine.
Yeah, yeah,
That's correct, that's easy to do.
yeah, I understand. Yeah.
Yeah, it's all like, at the summarize, like, dealing with those,
Yeah.
the positive, and it's time for the negative, flip it.
Mm-hmm.
Why do we flip it? Because absolute value, has the positive numbers.
Right. You know,
It's compensating, not a lot of that compensating for them.
it is. Yeah. Let me see what else I have. I think we're good. Let me just give y'all a little bit, one more tea, and then that's it. And y'all could go after that. Yeah, one last one. So yeah, man. All right, so look, given an absolute value function, right? So you want to solve for a set of inputs where the output is positive or negative, right? Here's how you do it step by step. Step 1, set the function equal to 0, solve for the boundary points of the set of the solution set. And step 2, test the points of or a graph to determine where the function's output is positive or negative. All right. And that's it. Y'all should be good to do your homework. All right.
Is it lose better than that or?
No, like August 3rd. Yeah.
Until August.
Yeah.
Okay.
Stop. So,
So
all right.
this one.
Let me submit it real quick. Let's see. So that mean I do that. Okay, not bad. Okay. So,
So this.
yeah. And negative. Right, okay, that's the Y value. So for -4 less than or equal to X. That means that X is greater than, or see, X is greater than or equal to 4. Well, greater than or equal to -4, so right here, this part. Of that Y value. So that Y value should be between 1 and -5.
Yes. But I did that one, but they told me now.
Let me see. I want to try between 1 and -5. Where that's bracket. That would be a parenthesis. Like that. And that should be the same thing with this one.
Mhm.
Right, this should be from 1 to infinity.
I think 9.
9?
Yeah.
No, infinity because it's an arrow. See,
Oh,
yeah, so this one should be from brackets 1 to IN.
no, 2, right? Negative
2, you're right. -2. Something like that. Thinking.
You see?
Yeah.
I do that one. They told me it's not this one.
It says the left endpoint must be. Yeah, we have it mixed around. So -5 to. So. -5. Right, because we're supposed to read it from bottom to top. Yeah. So -5 to 1 bracket. And then. This one should be -2 to infinity. Yeah, that sounds about right.
You see?
That the nice house on the hill, Chris?
Huh?
Trying to get the nice house on the hill?
I wish, man. Yeah, still struggling, man. Oh, hold up, let me.
But that, but then we put you washers.